Alright, so hello everyone, and welcome to the Prelim Physics 2023 July lectures. I'll start off the lecture by talking a little bit about myself. So, hello everyone, my name is Thamika. I graduated the HSC last year in 2022 with an ATAR of 99.30. The subjects that I did, the HSC subjects that I did, they were Physics, Chemistry, Math Advanced, Math Extension 1, English Advanced, and English Extension 1. Currently studying a pathway to med in Queensland, and in terms of fun, I do a lot of things for fun right now, but I guess I worked on Valorant when I did the slides, so I guess you can take that for one of the things that I do for fun. But I do a lot of stuff now that I moved into uni. It gives me a lot more freedom. But yeah, now that I've introduced a little bit about myself, I'll give a quick intro about Aton notes. So Aton notes. Since 2007, we've been offering heaps of free resources to make sure students just like you can thrive in their studies. So we've offered free lectures just like these ones since 2015. And these free lectures are in line with Aton Notes' mission to help students as much as possible. And so to do that, we have a ton of resources available for you guys. So here are just some of the things that we offer, and you can find pretty much everything at atonnotes.com. So if you want more info or tips on how to use these resources, you can check out the info doc under the resources section of this lecture page. We have free notes, free videos, free guides from past students. And if you have questions after the lecture, the best place to go would be the Q&A, where current and past students, just like me, can answer your questions. So if you're looking for even more support, we've got you covered as well. So there are a couple premium resources that we offer. We offer low-cost group and private tutoring, printed study guides, and online access to study resources with Ed Unlimited. So that was just a brief introduction about Aton Notes. And with that out of the way, we can get started on actually going through the lecture. So this lecture will be going through Module 1, Module 2, Module 3, and Module 4. So all 4 modules in this 2-hour lecture. So we won't be able to cover everything in depth, but this will just give you a brief overview and prepare you as you're going into your, end of year exams in year 11 and year 12 exams, and not year 12 exams, sorry, but like walking into year 12. So I'll first start off with a little bit of an overview. So looking at how to approach physics as a subject itself. So before you launch into studying, you need to know well what you're tackling with. So to do well in physics, you need to have strong and logical reasoning. You need to have a good mathematical basis as well to answer the calculation questions. And you need to be able to have a clear language and structure, so you're able to better communicate like the answer to your questions, because that's a big area where a lot of people actually lose marks, the long response questions, because in the new syllabus, the new syllabus has moved towards more of long response questions. So yeah, you need to be able to have clear language and structure. And the most important thing is, especially since you guys are in year 11, you guys need to be focusing on strengthening your weaknesses. And this doesn't really end when you go into year 12, but it's a lot more important in year 11. So you have a good foundation walking into year 12. You still need to focus on strengthening. You always need to focus on strengthening your weaknesses, basically. So ask yourself, where am I having trouble? A good thing that helped me at least, and it's unfortunate that I discovered this in year 12, but it was the use of a mistakes book. So after every exam or after every past paper I did, I would have a go through it and I would write down the questions that I got wrong and why I got them wrong. And I would always have a read of this mistakes book before I went into an exam or before I did a past paper. And it really helped me, because I kind of knew what the past mistakes that I made were, and they were fresh in my mind walking into the exam hall or the library hall or wherever I did my past paper or exam. And so I would be a lot more aware of not making those mistakes, if that makes sense. So common physics woes include the content itself, who do I look at, the school or the textbook, and the exams. So in terms of approaching physics content, try and use different sources. So there you can use your textbooks, Khan Academy, Hyperphysics. There's a lot of different sources that you can use, and always focus on understanding the content rather than memorizing stuff. Memorizing stuff, although it may seem good in the short term, a lot of questions will test on how you apply your knowledge. So memorizing the content won't help you when you're applying the content, because applying the content tests your understanding, not the fact that you've memorized itself. So always focus on understanding. And this can be done through formulating patterns, mnemonics, and different hacks that you can do for yourself. And try break down the content as well. Break them down into sizable chunks, and this will really help you when you're approaching complex topics. So when it comes to school exams, definitely prioritize what the school teacher says over the textbook, because ultimately schools have free reign over what they're going to test you on, right? And so what the textbook says, or what the content, the level to which content is covered in the textbook may not be the level to which content is covered in your school, and your school might test on stuff that's not seen in your textbook. So always, for school exams at least, always prefer the school over the textbook. And then, as I mentioned before, look over your past exam comments and guidelines, because this will really help you improve and better yourself. And always make sure to communicate with your teacher as well. This becomes especially important moving into year 12, because then your internal marks count towards your HSC as well. It counts 50% towards your final HSC mark. And so, yeah, always communicate with your teacher. Schools have specific ways, or some schools have specific ways they want you to express info. I know my school did. And so, yeah, make sure you do this and you have a good way of communicating with your teacher, especially when understanding the way you answer questions, especially for school exams. So, exam tips now. Doing questions. You never know you're wrong until you're wrong. So I always recommend that you do as much questions as possible, because it may seem repetitive initially, but after doing a variety of questions, you'll understand that what you're doing is you're exposing yourself to different varieties of questions. And by doing this, you are essentially preparing yourself for any type of question that you may encounter when you're walking into either your school exams or down the lane, the HSC. So always practice makes perfect, essentially. And the other thing is, for your exams at least, you need to understand the different question types that you'll be tested on. So you'll have multiple choice, short answer, and long response questions, and they test kind of different things. So to summarize in an exam, there are approximately 3 different question types: multiple choice, short answer, and long response. In the new syllabus, problem solving questions are more common. So the how and the why. So it's testing your understanding rather than testing whether you've memorized the content. So MCQ questions then. They're typically straightforward in the sense that they typically involve simple or complex calculations, but it's pretty straightforward. Simple data interpretation, and this is where your understanding of memorized facts will come into play. This is straightforward, but it's also challenging in the sense that these facts may seem like minor points, but if you don't remember them, that's already 1 mark gone, right? Because it's with some of these MCQ questions, it could be very hard to make calculated guesses, especially if they're testing your pure understanding of facts, right? And so another thing is, with MCQ questions, time management is very important. I wouldn't recommend for you guys to spend way little time on the MCQ. But personally, for me, I found that MCQ questions were where I could save a bit of time, so that I could spare more time towards the short answer questions. So every exam that you do will probably have like a recommended time limit for the amount that you should spend on MCQ and the amount that you should spend on short answer. I kind of spend it a little bit less than that recommended time on MCQ and a little bit more than the recommended time on short answer, just because for me personally, I found that short answer questions were a lot more difficult to get right than MCQ questions. So yeah, let's approach short answer questions now. So short answer questions, there's a huge variety of questions that you can be tested on. These are also typically straightforward in the sense that only straight facts are required, and it's not really asking you to put down they're not like long response questions where they need you to write a whole essay and draw whole diagrams and stuff. They're typically calculation questions or data interpretation. So these are difficult, however, in the sense that it's very easy to lose marks here. So this is where the bulk of lost marks come from. So calculation errors, missing logical links in explain questions, being succinct and concise enough, and actually answering the question. This is where most of those marks come from. So yeah, and over time it adds up because there's a lot of short answer questions in every paper. So yeah, approaching short answer questions, again, I think doing a lot of different types of questions will approach you to the different types of questions that they use to test on different content modules, and that makes it easy as well. But I think personally for me, One thing was I tried to break down the question myself. So I tried, if they gave me a sentence and that is the question, I tried to see where would they allocate the marks, right? So I would break down what they're asking of me into little fragments, right? So I would say, oh, they want me to show this content module. They want me to show understanding of this content module and apply it to get this answer. So then knowing that now, I would be able to solve the question effectively. This isn't like a foolproof method, right? Because I'm not going to be able to deduce what the marking criteria will be, but I will make an active effort to see where the marks could come from. This makes me more confident as well in actually answering the questions. So that could be a possible way that you guys might want to implement when you're answering questions. But ultimately, everyone has their own unique way of approaching questions, and whichever way you feel like will make you better at answering questions, that's the way that you should go. So next we have long response questions. So long response questions, they're pretty similar to writing mini essays. And they're essays in the sense that if you prepare for the topic that is asked, you have practically 3 marks. But then they're also difficult because you don't know what topic they're going to ask, especially in the HSC. And so if you're not prepared, you'll tank a lot of marks basically. So, and even if you are prepared, it's easy to lose marks for missing certain amounts of information, because oftentimes for me, I found that I would really know like some parts of the content information, but then I would leave out certain sections because I felt so happy that I knew the content that the long response question was testing on, if that makes sense, that I would forget to include the like additional information. The other thing is that long response questions are pretty tedious, so I would always recommend drawing a diagram, labeled diagram, and like, annotating the diagram. So oftentimes I have maybe 2 or 3 diagrams for a 9 marker, and it's just tedious to like plan out your response so you effectively answer each section. But it's a lot easier to do what I mentioned before, because long response questions, they'll kind of detail what they want you to give. So they're going to be like, I want you to show content understanding of this. Not word for word, but the sentence structure of the question will be much easier to like break down, and you'll be able to identify where the marks will come from a lot easier. And so these I find easier down to break down. And so I feel like approaching my HSC year, I was a lot better at answering these because I studied up the content. That's an important thing as well. But I was able to understand where the marks would come from a lot easier for long response questions than short answer questions. But yeah, so that was just a brief overview of like exam tips basically. But in terms of the year 11 course structure and requirements, the year 11 course, you have obviously working scientifically skills. So a lot of things will be tested on like your understanding of accuracy, reliability, validity, how you can improve those factors in an experiment. Those will definitely be tested in school exams as well. I know my school made a big deal about that aspect as well. But then you also have your content modules. So you have module 1, Kinematics, module 2, Dynamics, module 3, Waves and Thermodynamics, and module 4, Electricity and Magnetism. So we'll be going through all 4 in this lecture. All right, so let's make a start on module 1 then. So the structure of module 1 goes, you talk about motion in a straight line, and then you talk about motion in a plane. So motion in a straight line then, 1.1. What's the inquiry question? The inquiry question is, how is the motion of an object moving in a straight line described and predicted? All right, so in this inquiry question, students describe uniform straight line or rectilinear motion and uniformly accelerated motion. They conduct a practical investigation. So this is where that working scientifically skills comes in. They conduct a practical investigation to gather data to facilitate the analysis of instantaneous and average velocity. They calculate the relative velocity of 2 objects moving along the same line using vector analysis. They conduct practical investigations to record and analyze the motions of objects in a variety of situations in 1 dimension. They use mathematical modeling and graphs to analyze and derive relationships using between time, distance, displacement, speed, velocity, and acceleration in rectilinear motion. So you can see the stuff in blue. A lot of the stuff is practical work. So most of the stuff will be tested in school. Well, what I mean by that is going into the HSC, like this stuff will rarely be tested, and if they are tested, it will be like 1 to 2 markers, but this is assumed content for year 11 at least. So the main points of 1.1 then, understanding the concepts of time, distance, displacement, speed, velocity, acceleration, introduction to vector diagrams, so resolving vectors and drawing vectors, using the 3 motion equations, and a lot of pracs basically. But the pracs, with the pracs, as I mentioned before, you'll have to understand what reliability, validity, accuracy is, how you would improve methods of validity, how you would improve accuracy, and how you would improve reliability, your ability to conduct these experiments themselves and obtain good results. And so that stuff is like what you will be tested on practically in school. So then, let's go from the basics. So what is the difference between a vector and a scalar quantity? Scalars have a magnitude without a direction, whilst vectors have a magnitude with a direction. So velocity is a vector quantity. Velocity is a vector quantity. Speed is a scalar quantity. Displacement is a vector quantity because it has direction. And distance is a scalar quantity. So yeah, categorize the following as either vector or scalar quantities. Then I've kind of already done some of them for you: time, distance, displacement, speed, velocity, acceleration. With these questions, since this is a pre-recorded lecture, I am going to assume that you guys will pause the video and solve these questions down before I continue on with them. So I am not going to pause and wait for you guys to solve the video because you guys have the ability to pause it. I'm just going to keep going. So yeah, I'll pause for like a couple seconds so you guys have time to pause the video before I go through the answer. But yeah, so the answer to this question will be, well, scalar and vector quantities, I'll draw a table. The scalar quantities in our given values are speed, distance, and time, because time doesn't have a direction. And vector quantities in this case are going to be velocity, displacement, and acceleration. They're all kind of linked to one another, and they're all kind of based off of one another, and they all rely on distance. So with that being said, now let's look at this question. What is the difference between instantaneous and average velocity? So again, I'll give you guys a few seconds to pause the video and answer it, and then let's go through it. So instantaneous velocity refers to the velocity of an object at a specific moment in time. So a specific moment in time. Whereas average velocity refers to the average speed and direction of the object over a period of time. So like over the period of car A traveling from point 1 to point 2, that will be average velocity. Whereas the velocity of car A at 5 seconds into his journey, that will be instantaneous velocity. Because like, what is his velocity at that particular point, right? That will be instantaneous velocity. All right, so we'll go through a question then. A car travels along a motorway at 120 kilometers per hour. Another car travels at 70 kilometers per hour. How fast is the overtaking car as viewed from the car which is being overtaken? So wording can kind of get confusing in these things. I would recommend to just take it slow and like maybe reread it again. So how fast is the overtaking car as viewed from the car which is being overtaken? Right, so if we're going to do it that way, then we need to look at, so we're basically looking at what is the speed of the car that is traveling faster from the perspective of the car that is traveling slower. So in this case, the car that is traveling slower is going to be the car at 70 kilometers per hour. The car that is traveling faster is going to be at 120 kilometers per hour. So it's basically asking what is the perspective of this car's speed from this car's perspective. So if we're going to solve that, then it would simply be 120 kilometers per hour minus 70 kilometers per hour, which will equal 50 kilometers per hour. Why? Because technically, this car is going to be traveling 50 kilometers per hour faster than this car, right? And so from this car's perspective, it will appear that this car is traveling at 50 kilometers per hour. So that's how we would get the answer to that question. That's relative velocity. Now we can look at the tip-to-tail rule, which is, how you would draw vectors. So to draw vectors, to draw vector diagrams, to resolve vectors, always follow the tip-to-tail rule. So the tip of one vector should align with the tail of the second vector. It shouldn't be tip-to-tip rule or tail-to-tail rule. It should be tip-to-tail rule. That's how all vectors, vector diagrams are drawn and how vectors are resolved. So that's just a quick reminder. Now let's look at the three equations, right? So below the three equations are the ones that you will use a lot throughout your physics journey. So these are the Suvat equations. So these three equations are what you're going to be using a lot in your physics journey. So S is equal to UT plus half AT squared, V is equal to U plus AT, and V squared is equal to U squared plus 2AS. For this dot point, you must know what each of these symbols mean. So, well, I'll go ahead and explain what these symbols mean. So S will be equal to displacement. So that's displacement. U will be equal to initial velocity, not final velocity, initial velocity. So what the velocity that the particular object we're talking about starts with. T is just time in seconds. A is going to be acceleration. And then same, T is equal to time in seconds. V, which is the next variable because we have explained everything so far, V will be equal to final velocity. So those are what all those symbols mean. All right, so let's look at another question then. So a car travels north at 30 meters per second. The driver sees flashing police lights for a RBT and must slow down to 40 kilometers per hour. The car decelerates at 7 meters per second for 3 seconds. Does the car slow down enough to avoid a speeding ticket? So I'll give you guys a few seconds to pause the video and then we'll get started with it. So first thing that we do is we will convert the 40 kilometers per hour into SI units. So 40 kilometers per hour is equal to 11.11 meters per second. How do we do that? Well, the rule of thumb is you just divide kilometers per hour by 3.6 to get meters per second. And you multiply meters per second by 3.6 to get kilometers per hour. So 40 divided by 3.6, I'll just double check this. Yeah, 40 divided by 3.6 is equal to 11.11111 recurring meters per second, right? So that will be our final velocity. So V will be equal to 11.111 recurring. U will be equal to 30 meters per second. And A will be equal to negative 7 meters per second. So that will be, yeah, A will be equal to negative 7 meters per second because it decelerates, and T will be equal to 3 seconds. So what are we testing in this case? We're going to be testing if the final velocity will be equal to 11.111, right? Because that is our target final velocity. We want to slow down to 40 kilometers per hour. If it doesn't equal 11.111 meters per second, then we know that, if the final velocity is greater than 11.111, then we know that the car doesn't slow down enough to avoid a speeding ticket. So the car will get a speeding ticket, because if the final velocity is greater than this value, then it's going to be greater than 40 kilometers per hour. And so it won't slow down enough. So to solve this then, what we'll do is we'll just simply plug in the values, right? So V is equal to U plus AT. So do 30 plus negative 7 times 3, and we'll get 9. So our final answer will be 9. So V will be equal to 9. That means that the car is able to slow down more than the required speed, right? And that basically means it's safe. So if it must slow down to 40, then if it's below 40, then it will be safe, right? So 9 times 3.6 is equal to 32.4. So it slows down to 32.4 kilometers per hour within those 3 seconds. So if everything is all good, it is able to slow down enough to avoid a speeding ticket, because 11.111 is simply the threshold, the target that it has to beat. All right, so that was 1.1. Now we can move on to 1.2, motion on a plane. So the inquiry question here is, how is the motion of an object that changes its direction of movement on a plane described? Okay, for this inquiry question, students must analyze vectors in 1 and 2 dimensions, represent the distance and displacement of objects moving on a horizontal plane, describe and analyze algebraically, graphically, and with vector diagrams the ways in which motions of object changes, describe and analyze, using vector analysis, the relative positions and motions of one object relative to one another on a plane, and analyze the relative motion of objects in 2 dimensions in a variety of situations. All right, so then the main points of this summarized is, well, first of all, 2D motion, so X and Y points, the coordinates on a plane, projectiles and parabolic motion, more vector diagrams, and using the 3 motion equations a little bit more, and then graphs as well. So that's a quick summary of what this dot point entails. So 2D motion then. So now that there are 2 axes, X and Y, we need to label our vectors accordingly. So we have, so if we have velocity over here, every vector will have a horizontal and vertical component. That could mean that one of the components could be equal to 0, right? So if velocity has 0 Vx and some value for Vy, then we know that it's going to be a vertically orientated line, right? And the magnitude of its vertical component will indicate the magnitude of the line's vertical height, basically. That's because Vx is equal to 0, so it's not going to have a horizontal component. So everything can be drawn to have a horizontal and vertical component, but in some cases, one of those components can be 0. So we need to be able to label our vectors accordingly. So if this is our vector v, right, they will have a horizontal component Vx, and it will have a vertical component Vy. So that's labeling the features then. So additionally to this, we'll be using trigonometry to help calculate our vector values. So Vx is equal to v cos A, Vy is equal to v sin A. How do you get that? Well, let's let this angle equal to A. All right, let's let this angle equal to A. Sine A, right? Sine A is equal to opposite over hypotenuse. So sine A is equal to Vy divided by V. If I multiply both sides by V, then I get Vy is equal to V sine A. That is the vertical component. Same way now, I'll take this angle A and I'll do cos A. Cos A is equal to adjacent over hypotenuse. Cos A is equal to Vx over V. If I multiply both sides by V, I get Vx is equal to V cos A. That is that. All right, give me 1 second to plug my Mac in. All right, let's get started. So then how would we calculate the total velocity itself? So to calculate the total velocity, we can just do Pythagorean theorem, right? It's basically a right angle triangle. When we split it up into a horizontal and vertical components, you can see this, it just forms a right angle triangle, right? So we can just do V, the final component, is equal to Vx squared plus Vy squared, everything squared, and then you get that value and then you square root that value. So the square root of Vx squared plus Vy squared. Same way now, to find the angle, all we have to do is we know tan alpha is equal to Vy over Vx. So alpha is equal to tan inverse Vy over Vx. Same way we can use any other trigonometric value. So we can do cos inverse Vx over V and sine inverse Vy over V, if that makes sense. All right, so that is how to calculate every separate value. Moving on from that now, there are 3 specific scenarios in which NESA states in the syllabus to test on. So one of these scenarios is a boat on a floating river relative to the bank. The second scenario is with 2 moving cars. And the third scenario is an aeroplane in a crosswind relative to the ground. So let's take a look at how we should approach some of these scenarios. So when approaching questions like these, the most important thing to do is take note of all the information that has been given. So similar to how we solved this question where we took down all the data that we've been given, make sure to do that because it makes visualizing the question and the process of answering the question a lot easier. Next thing is always draw diagrams. So always draw like vector diagrams or force diagrams because that will help you guys a lot in terms of resolving the forces or the vectors. And then always set a positive and negative direction. This helps to identify which values that you've listed down in the information are positive and which values are considered negative. And then also remember what your end goal is. Always remember what the value you're trying to find out is, because sometimes you could just go like keep on rearranging values and keep on rearranging and end up going nowhere. So remember what your end goal is. So that being said then, let's go through a question. So a bus is moving 90 kilometers per hour west, whilst a car is moving 40 kilometers per hour north. What is the relative velocity of the car from the perspective of the bus? So this is kind of resolving vectors. So to solve this then, so we say a bus is moving 90 kilometers per hour west, whilst the car is moving 40 kilometers per hour north. So what is the relative velocity of the car from the perspective of the bus? All right. So to solve this, what you're going to do is, so you're going to draw 2 vectors, right? So what is the relative velocity of the car so we're looking at it from the perspective of the bus. Okay, so first we can calculate the magnitude of the relative velocity. So velocity is a vector quantity, so we need to have direction and magnitude. So how do I get this magnitude and how do I get this direction? Well, what you can do is you can draw your 2 diagrams, right? So the bus is going west, the car is going north. right? You can draw a line representing 90, right? Because the vector quantities we're drawing are representative of velocity. So we can draw a quantity with 90 magnitude going west and a quantity with 40 magnitude going north. And then we can like resolve those vectors, right? We can resolve those vectors by drawing like a vector, basically a line between the two of them to form a right angle triangle. And that line, the angled line within that right angle triangle, the longest side will be the relative velocity. So to calculate the relative velocity, we'll look something similar to this basically. So this side will be, well, the sides will be a bit flipped because we're moving west and we're moving north, right? But one of the horizontal side will be 90, the vertical side will be 40. So to solve v, the total velocity, we'll just do 90 squared plus 40 squared. And that will allow us to get 98.48, two four significant figures. How about direction then? So with direction, what you'll do is, you will basically do tan inverse 90 over 40. That will give you what you are looking for. So tan inverse 90 over 40, because you label your angle properly, so you do opposite over hypotenuse, tan inverse 90 over 40, and that will give you an angle of 66 degrees. So north, and then you turn 66 degrees east. So that is what your direction will look like. Similar to the formula that we looked at before, A is equal to tan inverse Vy over Vx. We just sub in the appropriate values in this case, and we'll get tan inverse 90 over 40 to get 66.03, which is approximately 66 degrees. All right, so let's look at the graphing now. So distance versus time graph then. Because distance is a scalar property, these graphs do not give any information about the direction of the object's movement. Even if the object does change direction, we simply focus on its speed and we cannot represent it changing direction, because even if it changes direction, its distance is still going to be increasing. So for these graphs then, think about these three things. What does the horizontal line represent? What does a straight line with a sloping descent represent? And what does the gradient represent? So take a bit, pause the video, have a go at solving this question, and then turn on the video again. So I'll give you a bit to pause the video. All right, assuming that you have paused the video now, we'll go through the question. So a horizontal line, right, a straight horizontal line will indicate that speed will be equal to 0. Why is that? Because distance will not be changing over time. So the rate of change of distance over time will be 0, because the horizontal line means that distance ain't changing over time. And so the rate of change of distance over time will be 0, and that is the formula for speed, and therefore speed will also be equal to 0. What does a straight sloping line mean? So a straight sloping line, right, that's essentially indicating a slanted line, right? So something like this, something like y is equal to x, right? That means that a straight sloping line would indicate, or a straight line at a slant would indicate that distance is increasing at a constant rate, right? That also, in other words, is the rate of change of distance over time is constant. And so, as per the formula for speed, the rate of change of distance over time, we have constant speed. That's what is represented. What does the gradient of the line represent then? Well, the gradient of the line will represent the magnitude for the speed, because the gradient is essentially the rate of change of distance over time. y2 minus y1 over x2 minus x1. Y in this case is distance, x is time. So it will represent the rate of change of distance over time. And so the gradient will directly represent our known value, or our unknown values for speed in this case. All right, so because displacement is a vector property, these graphs, so this displacement versus time graphs, do give information about the direction of the object's motion. So you can see there's a bit of a difference between the distance versus time graph. Here we also have the negative axis as well, because we can tell which directions it's going in, and we define which direction is positive and which direction is negative. So for these graphs then, what does a horizontal line represent? What does a straight sloping line represent? Again, a straight sloping line will be just a line at a slant, basically a straight line at a slant. And what does a straight sloping line that crosses the x-axis represent? So something that crosses the x-axis either in this direction or either in this direction. And then what does a gradient represent? So again, pause the video, have a go answering the question. Assuming you've already paused the video, I'll go through it now. So a horizontal line represents displacement and velocity. So it represents that displacement is the rate of change of displacement is equal to 0, again similar to the previous question, and therefore it also represents velocity as being equal to 0, because velocity is the rate of change of displacement over time, and a horizontal line displacement isn't really changing. What does a straight sloping line represent? So a straight line at a slant or a straight sloping line will represent, again, a constant change in displacement and therefore a constant velocity, because velocity is the rate of change of displacement over time. And so if the rate of change of displacement over time is constant due to the line being straight, then the velocity is also going to be constant. So then, what does a straight sloping line that crosses the x-axis represent? It just means that it will be at a constant velocity. It was kind of a trick question because it crosses the x-axis doesn't really mean that that it's the magnitude for it is going to be changing, but it will indicate that the direction has changed now. So it's constant velocity, but the direction that it's going in may have changed, right? Because it's initially traveling in the positive direction. It initially has a displacement in the positive direction, and then it's gone past the origin point into the negative direction. So that's what that would represent. What does a gradient represent? Well, similar to the previous question, right? The gradient will represent y2 minus y1 over x2 minus x1. In other words, the rate of change of displacement over time. And so by definition, that will be equal to velocity. All right, then, what is the difference between a line with positive versus negative gradient? If it has a positive gradient, that will indicate that it has a positive velocity because displacement is increasing in the positive direction. And if it has a negative gradient, so it's going this way, then it will have a negative velocity because technically displacement is increasing in the negative direction. And so it will have negative velocity. All right, so with that question out of the way, we can move on to the next one, speed versus time. So because speed is a scalar property, these graphs do not give any information about the direction of the object's motion. So then, similar to distance, that we did, the very first graph that we did. So then, for these graphs, what does a horizontal line represent? What does a straight sloping line represent? What does the gradient represent? And what does the total area underneath the gradient represent? So again, pause the video, have a go going through these questions. Assuming you've done that, we'll go through the answers now. So a horizontal line represents constant speed, right? Similar to how a horizontal line indicated constant displacement and constant distance. In this case, it means that speed isn't changing with respect to time, and so speed will be constant, so it will represent constant speed. What does a straight sloping line represent? Well, I could say it represents constant acceleration, but me saying that will indicate that it represents a constant direction for acceleration and constant magnitude for acceleration as well. So I have to specify that because speed is a scalar quantity, it will only indicate magnitude and not direction. And so it will only indicate constant magnitude of acceleration. And then what does the gradient represent? The gradient will represent the magnitude of acceleration, not the direction, because we don't have positive and negative values. Speed is technically always constant, or always positive, sorry. And then what does the total area underneath the graph, under the graph represent? That will represent the distance traveled. So like looking at the gradient is going from distance to speed, and looking at the area under the curve is going from speed to distance, if that makes sense. So, all right, we can move on now to velocity versus time graph. So because velocity is a vector quantity, these graphs do give information about the direction of the object's motion. And you can see again how the graph changes a little bit. So it goes from having one quadrant to two quadrants now, because we can have values in the positive and in the negative direction. So then for these graphs, what does a horizontal line represent? What does a straight sloping line represent? What does a gradient represent? And what does the total area underneath the graph represent? All right, so assuming you pause the video, we'll go through this now. So a horizontal line represents constant velocity. A straight sloping line will represent constant acceleration. So now we don't have to say constant magnitude of acceleration. We can just say constant acceleration because it will take into account direction. So then, what does gradient represent? Gradient will represent acceleration. What does the total area underneath the graph represent? That will represent total displacement. So again, we go from displacement to velocity by finding the gradient, and we go from velocity to displacement by finding the area underneath the graph. All right, so with that out of the way then, we can move on to a question. So a ball is thrown vertically into the air. So we have to draw a couple of things now. So draw a distance versus time graph of the ball's motion as it's thrown vertically into the air, a displacement versus time graph of the ball's motion, a speed versus time graph of the ball's motion, and a velocity versus time graph of the ball's motion. So assuming you pause this, I'll start going through it now. So we'll first go through a distance versus time graph of the ball's motion. So a distance versus time graph will look something like this. Distance will constantly increase as we throw it into the air, and then it will begin to slow down, right, as it reaches its apex. So we'll throw it down and it will slow down, right? So as it reaches its apex, it will reach its apex point, and then it will start to come back down, right? So it will start to accelerate again, and that's what you see with this type of acceleration. So it doesn't come back down, it instead keeps going up because distance is always increasing, because we don't take into account direction, right? So no matter what direction it's moving in, it's going to be increasing. And so it increases, slows down a little bit when the ball reaches its apex, and as it begins falling down and accelerating again, distance begins to increase as well. So that's what a distance versus time graph will look like. The next thing that we're going to look at is a displacement versus time graph. So a displacement versus time graph will be a little different. A displacement versus time graph will take into account distance. And so you'll have a similar increase, just like distance, right? It's going up, 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 up. But then after it reaches its apex, it will then begin to fall back down, right? So technically, the displacement, is increasing in the negative direction, right? But it's visualized in the graph as the ball falling down. So this is kind of what the trajectory of the ball will look like over time. And this is what the trajectory of the ball will look like with distance over time. So that's those two. Then we can look at the next scalar quantity, speed versus time graph of the ball's motion. So the speed versus time graph of the ball's motion will look something like this. So speed will begin a constant deceleration. What will the magnitude of that constant deceleration be? It will be 9.8. It will be decelerate constantly at a value of 9.8 because as we throw the ball, we're not exerting a force on it anymore. So it already has an initial velocity or an initial speed, and that speed is going to constantly decrease due to the force of gravity, right? And so it's going to decrease until it reaches its apex. Where at the apex or the top of its motion, right, the max height that it reaches, the speed or velocity, they'll both be equal to 0. And then after that, it will start accelerating in the downwards direction, right? But speed doesn't take into account direction. So it's just going to say that it's going to increase, speed is just going to increase at, again, a constant rate of 9.8. So that's the speed versus time graph of the ball's motion. We also have the velocity versus time graph of the ball's motion. So what will the velocity versus time graph look like? The velocity versus time graph will look like this. So the velocity versus time graph, it will essentially be the same as the speed versus time graph, except we take into account direction in this case. And so it will constantly decelerate at 9.8 until it reaches its apex point at 0. And then it will continue to constantly decelerate at 9.8 because even though even though the ball's direction changes, right, the magnitude of acceleration is always the same. And we can see how the ball's direction changes by looking at the quadrants. So initially it's moving up, so it's in the positive quadrant, and then after it reaches its highest point, it starts moving downwards. So now all the values are in the negative quadrant. So that's how you can tell apart the direction as well from a velocity versus time graph. All right, so those were those 4 values. We can now move on to Module 2. So it was a brief summary of Module 1. We'll now move into Module 2. Let's look at the structure of Module 2 then. So in Module 2, we look at forces, acceleration and energy, and momentum, energy, and simple systems. So let's go through that. So inquiry question, how are forces produced between objects and what effects do forces produce? So in this module, students using Newton's laws of motion describe static and dynamic interactions between 2 or more objects, explore the concept of net force and equilibrium in one-dimensional and simple two-dimensional contexts, solve problems or make quantitative predictions about resultant and component forces, and conduct a practical investigation to explain and predict the motion of objects on inclined planes. All right, so that basically summarized is going to be, you basically got to know Newton's laws and its applications, forces and net force, and forces on inclined planes. So my personal least favorite was inclined planes, but unfortunately you guys got to know it. So state Newton's 3 laws. Have a go at stating Newton's 3 laws. Pause the video, have a go at stating them, assuming you've already done that now. Law 1 will be the law of inertia, which states that any object which is in constant motion will remain in constant motion unless acted upon by an external force. So therefore, objects at rest will stay at rest, and objects in constant motion will stay in constant motion unless an external force is acting on them. So what is the second force? The second force is basically force is proportional to acceleration. F is equal to ma is the second law. Third law will be equal and opposite. That's the equal and opposite law. So every action or every action force has an equal in magnitude and opposite in direction reaction force. Every action has an equal and opposite reaction force, right? Equal in magnitude and opposite in direction. That is what that law 3 means. So those are all of Newton's 3 laws. That said, we can move into force diagrams again. So remember, forces can also be added together with vector diagrams. So in reality, we're going to use vector diagrams mainly for resolving forces rather than resolving velocity. That's where you're most commonly going to be using that. So always remember that forces can be added together with vector diagrams, just like you can see here. So any quantity can be taken into, we can split it up into components as long as you can represent it using vectors, right? So this force has a vector going in this direction. And so it has a horizontal component, Fx, and a vertical component, Fy. So assuming we set this angle to equal theta, the vertical component will be F sine theta, Fy will be equal to F sine theta, assuming this angle is theta, and Fx, the horizontal component, will be F cos theta. So that's how you do that. All right, so let's look at forces on inclined planes now. So the block is currently not moving on an inclined plane. What is the net force on the system? Is the normal force equal to the weight force? And is the force provided by friction equal to the force from the mass? Right? So I'll give you guys a second to pause the video, solve the question. Let's go through it. So what is the net force on the system? Well, we're given by the question that the block isn't currently moving. If it's not moving, right, objects at rest stay at rest, that means that the net force it's experiencing is 0, because if it experienced a force, it would begin to move, right? It would begin to accelerate because this block has mass, right? But it's not experiencing a force. And so that's why it's at stationary. So the net force is equal to 0. Is the normal force then equal to the weight force? What is the weight force? The weight force is gravity. Let's look at the vectors, right? Normal force is acting 90 degrees to this plane. So this plane, normal force is acting 90 degrees or perpendicular to it. Gravity, on the other hand, is acting just directly down. So directly vertical, acting down. So is the normal force equal to the weight force in this case? Well, the answer will be no. And why is that? Well, if you think about the net force being 0 in the system because it's stationary, that means that there has to be some force that balances out the downward force from gravity, right? There has to be something that balances out the downward force from gravity. Well, if we look at normal reaction force, we can split it into a vertical component and a horizontal component. So the vertical component of normal reaction force will be equal to gravity. So the normal component of normal reaction force and the normal component and the vertical component of normal reaction force, and I guess the vertical component of friction and mass, and all the vertical components of these 3 forces will be equal to and balance out the vertical component of gravity, right? And all the horizontal components will balance out one another as well. So if we're considering gravity is directly vertical downwards, that will be balanced out by all the vertical forces that go upwards. So this one, this small one, and this small one as well. So they will all balance out essentially. Yeah, so, one other thing is, I think I mentioned this incorrectly a little bit earlier. Friction will have a downwards force. So because friction is going downwards, slightly downwards, right, friction will have a vertically downwards force. So it's essentially the force from the mass, right, will counteract the force from friction. So I mentioned something wrong earlier. The force from the mass, the upwards force, the upwards vertical vector from the mass, will counteract the downwards vertical component of friction, right? So we'll just be left with the upwards vertical force from normal reaction force counteracting gravity in this case. So then is the force provided by friction equal to the force from the masses? Well, not necessarily. It doesn't have to be, because there could be other components like the normal reaction force, right? So if we look at the horizontal force over here, there's one horizontal force from there's a horizontal force from the mass, right? The horizontal component of that force. And then we also have the horizontal component of normal force and the horizontal component of friction. Both of them are balancing out the force from the mass, which means that friction doesn't fully equal the force from the mass, because both of the horizontal components from friction and normal reaction force contribute to cancelling out the force from the mass. So yeah, that's the reason why it's no. All right, so we'll take a shot at a hard question based on these in a second, but first we'll look at dot point 2.2. So forces, acceleration, and energy. So in this inquiry question, we look at how can the motion of objects be explained and analyzed. So in this dot point, students apply Newton's first two laws of motion to a variety of everyday equations, including both static and dynamic examples, and including the role played by friction, F, where friction is equal to mu naught Fn. So the frictional force is equal to mu naught normal force, or Fn. So the next dot point is investigate, describe, and analyze the acceleration of a single object subjected to a constant net force, and relate the motion of the object to Newton's second law of motion. And then the next dot point is apply the special case of conservation of mechanical energy to the quantitative analysis of motion, and then conduct investigations over a range of mechanical processes to analyze qualitatively and quantitatively the concept of average power. P is equal to change in E energy over time, change in energy, change in time, and P is equal to FV or FV cos theta, right? Or F parallel V or FV cos theta. So let's go. What does this mean then? Well, the main point of this summarized is we're going to be looking at power. We're going to be looking at the law of conservation of energy. We're going to be looking at friction. And we're going to be looking at more of Newton's laws and stuff. So friction, F is equal to mu naught N, is proportional to normal force following F is equal to mu naught N. So if we're pushing things together hard, then it makes them stick together even more. If pushing things together hard more makes them stick to each other more, then we can use Newton. So we can use our understanding of extra Newton then, using the second law as a formula. Delta F, so net force, is equal to MA, right? Sigma just means sum of in this case. So sigma F is equal to F net, right? Is equal to MA. So we're essentially just saying the sum of all the forces on a mass equals MA. So let's draw a diagram then. So how would we approach inclined plane questions knowing this? So let's draw, first of all, what I would recommend is you draw a diagram, and then you draw a free body diagram. So that means that you lay out everything, and then you draw all the vectors on it, right? Just like how we looked at a question like this. So we've drawn all the vectors, right? So you draw the free body diagram, then you resolve the vectors and you construct equations, and you apply Newton's third law and Suvat equations, and then you solve the question. So let's look at a question then. A 15 kilogram block rests on an inclined plane that has an angle of inclination of 35 degrees. What is the coefficient of friction on the surface? Well, let's go through this question then. So the coefficient of friction on the surface is what we're trying to look for. We have angle of inclination and we have mass of the block. So knowing this, pause the video, solve the question. Assuming that you have done that, we can get back to it. So I've drawn the body, so the diagram and the free body diagram as well, right? So I've drawn weight force, frictional force. I've drawn weight force downwards, frictional force that is preventing it from falling downwards. I've drawn normal force as well. They may not be proportional to their size, at least. That is just an issue with the way I draw stuff on my iPad. But yeah, in general, when you're drawing your diagrams in school, make sure that the forces, like the amount of centimeters or millimeters that you put into each line, should generally correspond to which one will be larger, right? So at rest, Wx is equal to frictional force. Why do I say that? Well, initially, right, we will only have W equals mg. but W equals mg has horizontal and vertical components. Now, I would recommend in your school exams drawing these with dotted lines instead of solid lines like I've done here. I just didn't have the capacity to draw dotted lines that were straight. So draw solid lines, right? Because in reality, there is no set force that's acting downwards like this. It's simply a component of another force that acts downwards like this. And that other force is weight force. So weight force is acting down this way. There has to be a force, right? If it's resting, there has to be a force. That means zero net force. So there has to be a force that counteracts this upwards frictional force. And frictional force is generated due to like us pushing down on it, right? So there has to be a force that is pushing down in the opposite direction to friction. That force will be Wx. So knowing that, then we can do Wx is equal to F, like FF, W sine 35, right? W sine 35, that's Wx. W sine 35 is equal to FF. So frictional force, or mu naught Fn, is equal to Wx, right? So we're trying to find mu naught. So we do Fn is equal to Wy then. So normal force is equal to Wy, right? Same direction. Normal force is equal to Wy. So normal force will be equal to W cos theta. So if normal force is equal to W cos theta, then we can just solve to find mu naught, right? Because we'll have normal force. We have an equation for Fn. We have an equation for frictional force as well. So what we have to do is we do mu naught is equal to frictional force over Fn. So we found out that frictional force, Wx, will be equal to W sine 35. And we found out that normal force, Wy, will be equal to W cos 35. So now we have mu naught is equal to W sine 35 divided by W cos 35, which will be equal to tan 35. And that will give us an answer of 0.7002 ... or approximately 0.70 to two significant figures. So yeah, that's what we would get. So let's move on to dot point 2.3 now. Momentum, energy, and simple systems. So the inquiry question here is, how is the motion of objects in a simple system dependent on the interaction between objects? So in this one, what we do is we conduct an investigation to describe and analyze one-dimensional or collinear and two-dimensional interactions of objects in simple closed systems. We analyze quantitatively and predict using the law of conservation of momentum, the conservation of kinetic energy, the results of interactions in elastic collisions, and we investigate the relationship and analyze information obtained from graphical representations of force as a function of time. We evaluate these effects of force involved in collisions and other interactions, and analyze quantitatively the interactions using the concept of impulse. And we analyze and compare the momentum and kinetic energy of elastic and inelastic collisions. All right. So the types of energy then. So we have kinetic energy and we have potential energy. So kinetic energy is the energy that an object has because it is moving. That's given by Ke is equal to half mv squared. This is on your formula sheet. Don't worry about memorizing it, but I'll say that by the time you reach your HSC, you will probably have memorized it by the amount of times you use it. So for something to have kinetic energy, it must have a mass and it must have a velocity as well. Potential energy, gravitational potential energy. The energy is the energy possessed by a body because of where it is. So if you're high up, it's like if you're high up, you're going to fall down. That's like that potential energy. And it's given by U is equal to mgh. And this is also on the formula sheet. It's cut off a little bit right now, but it says U is equal to mgh. All right, so then the total mechanical energy of a body is conserved if no non-conservative forces are acting on it. The total mechanical energy of a body is conserved if no non-conservative forces are acting on it. So the energy of the body that causes it to move remains constant if no forces suck energy away. The energy removed by forces, and this involves energy removed by forces like friction, air resistance, etc. Instead, the energy transforms, right? The energy doesn't get deleted, it transforms. Potential energy converts into kinetic energy and vice versa. So when something is falling down from high up, when it's at that point of being high up, right, before I let it fall down, so if I bring a ball up to here and I drop it, right, at this point, it will have higher gravitational potential energy than kinetic energy. And as I drop it, it's going to start increasing in speed, right? As it's increasing in speed, its kinetic energy is going to increase, and so its gravitational potential energy is going to decrease. So the total mechanical energy of the system is conserved. And then let's say it drops down to my laptop, right? And then I begin to pick it up and bring it back to the same height. As I'm picking it up, its kinetic energy is now going to be turned back into gravitational potential energy. So I'm going to keep increasing the gravitational potential energy as I bring it up again. And the cycle is just going to repeat, basically. So yeah, and this makes sense because you can technically say that by me bringing it up, my velocity is going to be in the opposite direction. And so it's just going to essentially add back into the GPE, because GPE, or U, gravitational potential energy, will work in the opposite direction to kinetic energy, or will have a negative correlation to kinetic energy, if that makes sense. So, all right. So the main points of 2.2 summarized are then collisions, the law of conservation of energy plus momentum, and impulse. So let's look at collisions then. So there are two types of collisions. We have elastic and inelastic collisions, and they describe what happens to the energy of a system. So in elastic collisions, there is no loss of kinetic energy. In inelastic collisions, there is a loss of kinetic energy, but kinetic energy is transformed into something else, like sound, heat, etc. So a quick question then, what can kinetic energy be transformed into in inelastic collision? So I kind of already mentioned that earlier. Kinetic energy is then transformed into things like sound, heat, and other types of energy as well. So in a collision, so if you imagine a car crash, it's going to be very loud, and the metal that's involved is probably going to be very hot, right? Because the collision has occurred. So that's where energy is going to be transformed into. All right, so then what happens to momentum in elastic and inelastic collisions? Momentum, right? Well, okay, well, let's see. Well, it's kind of a trick question. So if you remember back to the law of conservation of momentum, it says momentum always has to be conserved, right? That basically means that the momentum in both elastic and inelastic collisions remain the same throughout. So no matter what happens, the momentum is always conserved. The only difference is that kinetic energy isn't conserved in inelastic collisions, where it is conserved in elastic collisions. So to answer this question better, in inelastic collisions, common forms of energy that kinetic energy can be transformed into includes heat and sound. If you ever start thinking about a car crash, when there's a crash, you hear it, and sometimes the cars can catch on fire, right? Heat. So that's that. Let's look at impulse now. So impulse is just the change in momentum of an object, and this has to be caused by a force. So delta P is equal to Ft. Impulse is equal to change in delta P is equal to Ft. So an object with mass 2 kilograms then is traveling north at 5 meters per second, turns around and then travels south at 3 meters per second in 0.2 seconds. Find the force required to enact this change. So have a go at doing that question. To answer it then, first I will write down my formula. F is equal to ma, right? And what is a then equal to? A is equal to the change in velocity over time. So F will then be equal to m delta v over t. Then I can say F is equal to, if I sub in all the values now, 2 times 5 minus, so final minus initial velocity, right? I can sub them around however I want to sub them, right? So if I label 5 as being my, 5 north as being my positive and south as being my negative, I can be like 5 minus 3 divided by 0.2. What matters is the direction that I say at the very end, right? So I'll get 2 times 40, which will be 80 newtons, and then I put my direction as south. Why do I put it as south? Because, well, to enact this change, to make the mass turn south, I need to induce a force south, essentially. So that's the reasoning behind that. All right, so that is that question. Yeah, all right, moving on now. We can move on to module 3. So module 3 is waves and thermodynamics. All right, so the structure of module 3, we first look at wave properties, and then we look at wave behavior, and then we look at sound waves, the ray model of light, and finally thermodynamics. That's structure module 3 in a gist. So let's look at 3.1, wave properties. Inquiry question goes, what are the properties of all waves and wave motion? So in this dot point, right, students conduct a practical investigation involving the creation of mechanical waves in a variety of situations. conduct practical investigations to explain and analyze the differences between waves, construct and or interpret graphs of displacement as a function of time and as a function of position of transverse and longitudinal waves, and relate the features of those graphs to wave characteristics. Students will also be expected to solve problems and or make predictions by modeling and applying the relationships to a variety of situations. All right, that being said, we can sum it up. So a summary of this will essentially be just look at and understand the differences between mechanical and longitudinal waves and be able to talk about basic wave diagrams and be able to deduce information from basic wave diagrams and look at the anatomy of waves as well. All right, so mechanical and longitudinal waves. Mechanical waves. Mechanical waves rely on particle interactions to transport energy with no mass transfer occurring. Whereas longitudinal waves are where particles oscillate back and forth in the same direction as the motion of the wave. So a common experiment that you guys might have done in school if you haven't done it already, or an experiment that you guys might do if you haven't done already, is going to be the slinky experiment. So we'll be given a very large slinky and be able to, and the purpose of the experiment will be able to demonstrate or model transverse and longitudinal waves using a slinky. So to model a longitudinal wave, you will kind of attach one side to a wall, and then you will pulsate your arm like back and forward essentially. And by repeating that motion, you'll be able to have compressions and rarefactions, and compressions and basically areas of non-compression or decompression, rarefactions. So by doing that, you'll be able to emulate a longitudinal wave. Same way now, if you attach it to one end or get your partner hold it, you can now move your arm up and down to mimic the what a wave will look like, what a transverse wave will look like essentially. So this will be like one amplitude from the center line to the crest, same with the center line to the trough, right? And this will be like one wavelength, right? And yeah, you can model the properties using that. So with that being said, then we can move on to wave anatomy. So wave anatomy is looking at a couple of things, right? So you need to, in these images, you need to be able to deduce and identify the trough of a wave, the crest of a wave. So you need to be able to look at this and say that these pointy bits are going to be the troughs of these depressions are going to be the troughs of the wave, and these pointy bright lines are going to be the crests of the wave, right? In other words, the pointy tops, these parts, are going to be what you know as the crest of the wave, and these bottom parts or what you're going to know as the troughs of the wave. From here, or from here to here, or from here to here, that's going to be equivalent to one wavelength, right? So it goes up once and it goes down once, that's one wavelength, or it goes once and once, one wavelength. And the amplitude will be equal to the distance from this midline to either a crest or a trough. So that is basic wave anatomy. And now we look at wave formula, right? The essentials. So T, capital T, is the period of the wave, how long it takes to repeat once, and that's measured in seconds. Frequency is equal to 1 over T. It's the frequency of the wave, and that's represented by F. And that's basically talking about essentially how many times it repeats in 1 second. And this is measured in hertz. Lambda is the wavelength of the wave, and that's how physically long each repetition of a wave is. Right, so it's represented by lambda, as you can see over here. And the velocity of a wave can be given by v is equal to f lambda, right? Because if you think about the units, right, lambda will be measured in meters, because it's talking about length, right? And f will be measured in seconds to the power of -1, or 1 over seconds, because t is measured in seconds and frequency is 1 over t. So essentially what we're doing is we're multiplying meters by 1 over s. So m times 1 over s, that's m divided by s, and so we have meters per second. That's how that makes sense. So don't worry, because you've been given all these formulas on your data sheet. Just know they exist and be briefly familiar with the formulas. All right, we can now move on to 3.2, wave behavior. So in this inquiry question, we look at how do waves behave? So in this inquiry question, students explain the behavior of waves in a variety of situations by investigating phenomena. Students will conduct an investigation to distinguish between progressive and standing waves. Students will conduct an investigation to explore resonance in mechanical systems and their relationships. All right, so that summarized is basically students will look at wave behavior. Students will look at standing waves plus resonance and real life scenarios and applications. So for me personally, I had to do like in year 11, I remember doing this project where we had to craft our own instrument and we had to talk about the physics behind the sounds and it makes a resonance and harmonics and stuff. So yeah, that was pretty fun. And you guys might do that in year 11 as well. So the main wave behavior that we're mostly concerned about is reflection, refraction, diffraction, and superposition. So looking at this diagram then, have a go naming the wave behaviors that you see below. Take a second to pause the video and have a go at naming them. All right, assuming that you guys have done that, let's go through the answers then. So number 1 will be reflection, number 2 will be refraction, and number 3 will be diffraction / superposition. So there's going to be wave interference as well, but I'll go through it in a bit as I explain these. So reflection essentially hits the plane and it bounces off. That's reflection. Refraction is where it changes direction, right? So the light appears to bend, right? So it hits it and then the angle of refraction is less than the angle of incidence in this case. So it appears to bend, right? And then it leaves, so its emergent angle is the same as the angle of incidence. So as it leaves, it looks like it's bent a little bit. So that's refraction, right? As it passes from a less dense medium to a more dense medium or a more dense medium to a less dense medium. So as it passes through mediums of different density, it will refract, right? And then we also have this. So this is where one concurrent wave is going to hit 2 slits, right? And it's going to create 2 point source waves. So point source waves are, for example, if we have a still basin and I disturb the water a little bit by taking like a pin and pricking the water surface, that will create like circular ripples going outwards, right? That's a point source wave. So this will create point source waves. And as you can see, the wave fronts are interacting with one another, right? The wave fronts are crossing one another. That means that these waves will interfere with one another. And there are a couple ways that waves can interfere with one another, or actually 2 ways. So they can undergo constructive interference or they can undergo destructive interference. A couple different ways that they can go through it. So there's constructive and then there's destructive interference as well. So what are the 2 of them? Like how do we distinguish between the 2 of them, right? So to distinguish between the 2 of them, basically constructive interference, with constructive interference, what you will do is you will add the amplitudes of the 2 waves that are undergoing interference to one another. And this will appear, so if it's light, basically, these waves will appear brighter. If 2 light waves will interfere with one another and undergo constructive interference, the resultant light wave will be brighter. Same way now, if they can undergo destructive interference, and so then we will, what we'll do is we will we'll subtract the amplitudes from one another. And so if we take an example, in this case, light, it will appear darker. Or in terms of sound, the sound will appear louder if it's constructive interference and softer or quieter if it's destructive interference. Now you might ask, how does one thing undergo constructive and how does one thing undergo destructive interference? Well, if I go back to the wave diagram, right, we have crests and troughs. If 2 things interfere, that means we have another wave oscillating like this that interferes with it, right? So let's take the secondary wave. If this secondary wave has crests that align in the same time or the same place as the crests of this wave, right? So the crest of this wave aligns with the crest of the secondary wave. Then when these 2 waves interact, it will undergo constructive interference because the waves are aligned. If they're not aligned, however, so that would mean that the crests don't align with one another, or if they're perfectly unaligned, and to be perfectly unaligned, essentially, your troughs have to align with the crest of another wave. So in this secondary wave now, its lowest point occurs at the same time as this wave's highest point. Then you can say that they're perfectly out of line. And so it will undergo perfect destructive interference. And so the amplitudes will be fully subtracted from one another. So that's the difference between constructive and destructive interference, and what different scenarios cause them to occur. So knowing that, then in this case, these waves will undergo both constructive and destructive interference. Constructive interference, you can also refer to that as superposition. So we have diffraction and superposition occurring. Diffraction is like the bending of light of waves as it passes through or as it bends around obstacles, right? So that's diffraction, another wave property. But yeah, those are the the 3/4 wave behaviors in this diagram below. And now we can look at standing waves. So standing waves are a very special case of wave behavior. Standing waves are what happens during standing waves is that the constructive and destructive interference occurs at the same point each time, creating what appears to be a stationary wave. So if you can look to see here, the blue and the red wave are moving, right? The red wave is going to the left and the blue wave is going to the right. Even though these two waves are moving, because of the way that they're moving and the scenario that it's constructed in, the resultant wave, the net wave that is produced, so the wave in black line, it appears to be stationary, right? It doesn't appear to be moving. It appears to be fully stationary, right? And that's just like a weird phenomena, I guess. So that's what standing waves are. And we can label different points on a standing wave. So we have 2 points. We have nodes and we have antinodes. So nodes, these are the points on a wave which are not oscillating. So if we go back, right, or you can see here, these points, these dotted red points, they're nodes, the points that are not moving, and they're now hence called stationary. Antinodes, however, are the opposite of nodes. These are the points on the wave which are moving with maximum oscillation. So these points are considered antinodes. So like this center point that has maximum oscillation in it, right? And so that will be considered an antinode. Similarly, this will be considered an antinode, maximum oscillation, right? This will be considered an antinode, maximum oscillation. What won't be considered an antinode is this point over here, right? Because that doesn't have maximum oscillation. It only oscillates a little bit less than this point, which is maximum oscillation. So whichever point moves the most, that's kind of the antinodes. So oftentimes, or in every case, they're going to be halfway between a node and another node. So halfway between this point will be an antinode. Halfway between this point will be an antinode. Halfway between these 2 points will be an antinode. And that will continue on, similar trend. All right, so let's look at resonance now. So when a system is excited by a driving force, the system will vibrate at the frequency of the driving force or driving frequency. Resonance is the tendency of a system to respond more strongly to inputs of a certain frequency, known as its natural frequency. When the driving frequency is close to the system's natural frequency, we see an increase in the amplitude of motion. So here, everything that's bold is like key points here. So we have a concept called driving frequency. And so we also have natural frequency. And when driving frequency, so the frequency that we supply to it by a driving force, is close to the system's natural frequency, we see an increase in the amplitude of motion. And oftentimes when that amplitude of motion increases enough, that object can like break, basically. So this is what opera singers will use to break glass, essentially, because they will sing at that they will sing and provide a driving frequency that is close or equal to the natural frequency of the glass, and therefore that will result in an increase in the amplitude of motion, and therefore it will cause the glass to vibrate and shatter. So we can move on to the next point now, 3.3, sound waves. So in this inquiry question, we look at what evidence suggests that sound is a mechanical wave. So in this stop point, students conduct a practical investigation to relate the pitch and loudness of a sound to its wave characteristics. Students model the behavior of sound in air as a longitudinal wave. Students relate the displacement of air molecules to variations in pressure. Students investigate quantitatively the relationship between distance and intensity of sound. Students conduct investigations to analyze the reflection, diffraction, resonance, and superposition of sound waves. students investigate and model the behavior of standing waves on strings and or in pipes to relate quantitatively the fundamental and harmonic frequencies of the waves that are produced to the physical characteristics. And then students analyze qualitatively and quantitatively the relationships of the wave nature of sound. All right, so that's summarized. Basically means we look at sound wave behavior, standing waves continued, and more real-life scenarios and applications. So remember, sound is a longitudinal wave. Within longitudinal waves, we can look at wave anatomy. So these points of high compression, they're called compressions, and these points of low density are called rarefactions. So low pressure, high velocity, high pressure, low velocity, right? Direction of travel, we can see direction of travel going this way. So that's a longitudinal wave. So within a longitudinal wave, we have something called beats, right? Beats are essentially, so we can hear when these two sound waves collide, we can hear beats occurring, right? This resultant wave in blue, that could be the beat frequency. To calculate beat frequency, we just find the magnitude of the difference between the two frequencies of the two waves, essentially. So how out of line they are, basically, and so we can calculate the beat frequency. And then the other concept we can look at is a Doppler effect. The formula for the Doppler effect is the observed frequency is equal to the original frequency times the velocity of the wave plus the velocity of the observer divided by the velocity of the wave minus the velocity of the source. So what is the Doppler effect? Well, if you think about it, right? Like if you think about an ambulance rushing towards you as you're an observer, as that ambulance rushes towards you, it's going to be emitting quite a high-pitched siren, right? And as it's rushing past you, so it's past you now, that siren is going to go from sounding high-pitched to low-pitched all of a sudden, right? Why does that occur? Well, that occurs, or like that phenomena is explained by the Doppler effect. So by the Doppler effect, it's kind of talking about how as the ambulance is rushing towards you, the observer, the sound waves that it's producing from the siren are going to get compressed. And so it will appear high-pitched, right? And as it's past you, now we can look from the perspective of this observer, right? Because the ambulance is past this guy. As it's past you, the sound waves that the siren is producing is going to be more like elongated or less compressed, right? It's going to be more stretched out, essentially. Because it's stretched out, that will manifest itself. We will process that information as a deeper sound compared to here, where we will process that information as a more high-pitched sound. And so that is the basis for the Doppler effect. And we can solve that using V wave plus V observer divided by V wave minus V source times frequency. All right, so Giulia stands still on the side of the road. If a fire truck approaching her at 30 meters per second has a siren that produces a noise at 350 hertz, what frequency will Giulia hear, or Giulia? So she's standing still on the side of the road, right? So the velocity of the observer will be 0, and a fire truck is approaching her. So it hasn't passed her yet, it's in the process of approaching her. Knowing this then, have a go at solving this question. So, assuming that you guys have paused the video and solved the question, and if you guys have any questions, by the way, make sure to put it down in the live chat below because I will be monitoring it during the duration of this lecture, basically. Let's go ahead and solve this. So the first thing that I will do is I will write down the formula, right? And then I will look for what am I looking for? Well, I'm looking for, thankfully, I'm just looking for this value. So I don't need to rearrange the formula because I'm given the values to solve this. All right, so knowing that then, I will plug in all the values. So F is equal to 350, right? Because they give us 350 hertz. The siren produces a noise at 350 hertz, right? And that is times 340, which will be the speed of sound. 340 plus 0. So V observer is going to be 0 because she's standing still on the side of the road. And V source will be 30 because the fire truck has, which is the source of sound, will have a velocity of 30 meters per second. And so I will minus 30 from that. That will cause me to get a frequency of 383.87096 or 380 hertz to two significant figures. Now, I was thinking about this from a sanity perspective, right? Because it's very good to sanity check your answers. If the ambulance is rushing towards us, then we're going to hear a high-pitched sound because the sound waves are going to be more compressed. As it's rushing past us, we're going to hear a lower-pitched sound because the sound waves are going to be more, the the sound waves are going to be more stretched apart, right? So it makes sense that the frequency that we hear is higher, because if the frequency we hear is higher, then we're going to hear a higher pitched sound. So that's sanity checking stuff. Another tip that I would like to mention is I always recommend that you guys solve the question algebraically first before subbing in the values. So I always recommend that you sub in the numerical values at the very end of your question as opposed to before, because it's a lot easier to move numbers, like to move algebraic values around, than numbers like these, right? Because imagine we had to move a whole bunch of equations around to find the velocity of the observer. So we were given everything, but we had to find the velocity of the observer. What would be very confusing, right? Moving everything around to let the velocity of the observer equal something, right? Because we don't know which value this 340 is, we don't know which value this 340 is, so we'll be moving random values around, and it's a lot easier to make a calculator error as we go from different steps to steps, right? And this is if we subbed in values initially. Whereas with this question, it doesn't really apply, because we don't really do anything with this question. We just sub in values, right? But in questions where you have to manipulate the equation to get the answer, I always recommend manipulating it algebraically and then subbing in the values, because it minimizes the chance of making a calculator error. And even if you do make a calculator error, it's a lot easier to find out where you made the error, because you've only subbed in the numerical values at one point right before you get your answer. So you know that if you made an error and it's not a calculator error, it's probably an algebraic error, and those are a lot easier to spot than numerical errors or calculator errors. So yeah, that's another tip that I recommend you guys follow. But with that said, now we can go into harmonics, right? So harmonics and overtones are different versions of standing waves due to differences in energy and hence frequency. So we have the fundamental first harmonic looking like this, the fundamental second harmonic looking like that, so n equals 2, and that will have a full wavelength. The fundamental third harmonic, harmonic has like 1.5 wavelengths, and the fundamental fourth harmonic, which has 2 full wavelengths. So those are the fundamental harmonics from the first to the fourth. And the next point is that harmonics and overtones appear different depending on whether the string is fixed and whether the pipe is closed or open. So what does that mean then? Well, let's have a look, right? So we have the third harmonic, first overtone, fifth harmonic. So we have a diagram over here basically for each of the harmonics, and have a go at stating the total number of wavelengths for each of them. Kind of gave it away already by stating them over here, but take a minute to write it in over here, right? These blank spaces. For each of the harmonics, state the total number of wavelengths. So again, I'll give you guys a few seconds to pause the video. So I hope you paused the video already, and then we'll get into answering it. So, all right. So, so this one will have 1/4 of a wavelength, right? So the first harmonic will have 1/4 of a wavelength. So yeah, first harmonic will have 1/4 of a wavelength. And then that's if the pipe is closed and the string is fixed, right? So you can see the string is fixed and the pipe is closed. If the pipe is open then, so the string can't be fixed, then the first harmonic will have half a wavelength in it, or the fundamental harmonic will have half a wavelength in it. Let's take the third harmonic now. So the third harmonic will have 3/4 of the wavelength if it's closed and the string is fixed. If it isn't closed and the string isn't fixed, then the second harmonic, in this case, will have one whole wavelength. This is the fifth harmonic now. Fifth harmonic will have, assuming that it's closed, we can only move on to the fifth one. The fifth one will have 5/4 of the wavelengths. The seventh harmonic, assuming that it's again fixed and the pipe is closed, will have 7/4 wavelengths. And the ninth harmonic will have 9/4 wavelengths. Compared to if it's open and the string isn't fixed, where the third harmonic will have 1.5 wavelengths, the fourth harmonic will have 2 wavelengths, and the fifth harmonic will have 2.5 wavelengths. So yeah, there's a big difference depending on whether the pipe is closed or open. So keep that in mind as well. All right, so with that out of the way, then we can move on to dot point 3.4, the ray model of light. So in this inquiry question, we look at what properties can be demonstrated when using the ray model of light. So in this thing, what we do is students conduct practical investigation to analyze the formation of images in mirrors and lenses via reflection and refraction using the ray model of light. Students also conduct investigations to examine qualitatively and quantitatively the refraction and total internal reflection of light. Students predict quantitatively, using Snell's law, the refraction and total internal reflection of light in a variety of situations. Students conduct a practical investigation to demonstrate and explain the phenomenon of the dispersion of light. Students conduct an investigation to demonstrate the relationship between inverse square law, the intensity of light, and the transfer of energy. Students solve problems or make quantitative predictions in a variety of situations by applying relationships. So, the main points of that essentially are we look at light ray behavior, mirrors and lenses, and even more real life scenarios. All right, so let's look at Snell's law. So light ray behavior, Snell's law. So Snell's law talks about the relationship between the angle of incidence and the angle of refraction based on the refractive index, and the given refractive index n is equal to air is equal to 1. So Snell's law is denoted by n1 sine I is equal to n2 sine r, or n1 sine 1 is equal to n2 sine 2, right? The same values essentially. And you can see how it's describing the properties of refraction here as it refracts from one medium to another medium. So let's look at total internal reflection now. So when the first medium is greater, the refractive index of the first medium is greater than the second medium, right? Light bends towards the normal. You have a critical angle now, that is I is equal to sine inverse 1 over n. And that's essentially talking about the incoming ray. So it's saying how the incoming rays bend to travel along the boundary. Any angle greater than this critical angle causes total internal reflection. So you can see over here, right? When the light ray is traveling at an angle less than the angle of incidence, it will parts of it will be refracted, parts of it will be reflected along this boundary between the two mediums as well. When it's directly at the critical angle, it will fully be forced to travel along this boundary between the two mediums. So it will fully be reflected along this boundary between the two mediums. And the moment that it is greater than the critical angle, it will undergo total internal reflection, where none of it will be refracted and all of it will be reflected within the boundary itself. So all of it will be reflected by the boundary, so within medium 2. So that's total internal reflection. I think the important thing here is knowing the formula for Snell's law, which is on your data sheet, and the critical angle. All right. So now let's look at inverse square law. So what is inverse square law? Inverse square law basically states, or it's a law talking about how the area of light increases by the square of the distance. Energy transfer is constant, and so comparing intensity at 2 points, you can go by I1R1 squared is equal to I2R2 squared. And I is proportional to a value over R squared. I is proportional to 1 over R squared, essentially. And that's what this top says. So this diagram says how, like, you have a square of 1 on 1, and as we increase from a distance of 1 to a distance of 2, the area has increased exponentially, basically. So it goes from 1 to 4. And then as we increase the distance again, it has increased exponentially by a square factor again, to go from 1 on 4th intensity of the original light to 1 on 9th the intensity of the original light. So the intensity of light decreases exponentially, or it decreases by a square factor as we increase distance. And that's denoted by the I is proportional to 1 over R squared factor. So as we're 3 meters away from it, we'll have 1/9 of the original intensity, if that makes sense. All right. So now we can look at mirrors and lenses. So with mirrors and lenses, you should look at the two different lenses, right? They have different properties. right? So if we have a biconvex lens, right, or a convex lens, so it's convex on both sides, right? As light rays enter this convex lens, it'll be fine focused, or like the light rays will be refracted to focus on this singular point. And that's essentially what magnifying glasses do. They focus the light rays on a singular point. So what will end up happening is it will magnify that point essentially. So it will appear magnified, but also magnify the energy that light is carrying to be focused on that singular point. That's why if you hold the magnifying glass through, like if you let sunlight shine through a magnifying glass and you put it next to paper, it will burn through the paper, or it will cause the paper to be set on fire potentially, because it focuses all that energy on the sheet of paper. Same way with a convex lens, it does the opposite. So a convex lens, instead of magnifying it, it kind of zooms things out, I suppose. So a concave lens, it will now scatter the light outward. So instead of focusing the light on a single point, when light rays enter a concave lens, what will happen is it will end up scattering that light outwards. So that's what the concave lens will do. So those are lenses. We also have mirrors now. So with a convex mirror, as light enters, it will bounce off in this particular angle, right? It will kind of just reflect off the convex, the shape, right? The outwards curvature. Whereas if it enters a concave mirror, it will reflect in the opposite direction due to the inwards curvature of the concave mirror. So over here, it will reflect upwards. Over here, it will reflect downwards. So it will reflect in the opposite direction as to what it would do in the convex mirror, essentially. And in terms of how you can be tested for this, there's not much. You could be asked to draw what it might look like in an exam, right? You could be asked to draw. But I was mostly tested on this in school in practical work. So in my school, they just gave us a practical sheet and was basically like, just have fun with mirrors and try to draw diagrams. And the teacher just checked competency afterwards. I don't even think it was grade or went towards my grade in any way. So yeah, I wasn't really tested too much on this. I've come across a couple of questions where they've asked you to draw what the reflected angle might look like. But the questions that I got, they didn't even ask us to specify what this angle might look like. They just asked us to draw an estimate of what the reflection would look like. So yeah, that's all that there is to mirrors and lenses. And so now we can move on to dot point 3.5, thermodynamics. So in this inquiry question, we look at how are temperature, thermal energy, and particle motion related. So in here, students explain the relationship between the temperature of an object and the kinetic energy of the particles within it. So students explain the concept of thermal equilibrium. Students analyze the relationship between the change in temperature of an object and its specific heat capacity through the equation Q is equal to mc delta T. Students investigate energy transfer. Students conduct an investigation to analyze qualitatively and quantitatively the latent heat involved in a change of state. Students model and predict quantitatively energy transfer from hot objects by the process of thermal conductivity. Students apply relationships to solve problems and make quantitative predictions in a variety of situations. And that is essentially dot point 3.5 thermodynamics. So a summary of this then can be, students will look at heat, temperature, energy, thermal equilibrium. Students will also look at latent heat and thermal conductivity. And students will try and use calculations following the formula Q is equal to mc delta T or Q is equal to mcat. So let's look at thermodynamic terms then. The kinetic energy of a particle is how much vibrational movement each particle has in a certain area. More kinetic energy equals more vibration and vice versa. Temperature then, so more kinetic energy can also be attributed to greater heat. So if something is more hot, then the particles will be moving more vigorously, so they'll be vibrating more, and therefore each particle will possess more kinetic energy essentially. Temperature is a measure of the average kinetic energy of each particle. And thermal energy is the total energy an object has due to all particles vibrating. Thermal equilibrium is when there is no net flow of heat. So if you put a hot coffee in an ice bath, right? two very different temperatures. One has a lot more heat than the other one. The hot coffee will start reducing its heat, like giving its heat to the ice, causing the ice to heat up. Sorry, and eventually they will reach a thermal equilibrium where they won't exchange any heat. So there will be no net flow of heat because each of them will be at their respective temperatures where they won't need any more heat, essentially. So yeah. So we have different ways of transferring heat, right? So we have conduction. This is the contact between solids where particles bump into each other, transferring kinetic energy, right? So you can see conduction here. That's where heat spreads throughout this solid handle, right? Because one is hot, and this causes the hot particles. They'll have more kinetic energy, more vibrational energy. Therefore, these particles over here will, as they're heating up, they will begin to bump into surrounding particles, causing them to vibrate more vigorously as well, and therefore causing them to heat up as well. And this will form like a chain reaction, essentially spreading throughout the entire handle. That is conduction. You also have now convection. Convection occurs between liquids and gases, and that is the physical movement of particles from one place to another. So that's convection. So convection is like you have convection currents, right? So let's say, so over here we have a convection current forming because we have it being heated up over here, right? We have it being heated up, so hot air rises, right? Because hot air is lighter because the particles move around more, it's considered less dense. So hot air rises, right? So this hot air will begin to rise to the top, causing the cold air to sink to the bottom. As that happens, the cold air now will begin to be heated by the stove. And so now the cold air will warm up, whereas the warm air will begin to cool down. And so now the warm air initially will become the cold air, and the cold air initially will become the warm air, and then that cycle will repeat again. And so that cycle will continue repeating, and that is what we call convection currents. And that is heating through convection. We also have radiation now. Radiation is where the thermal vibration of an object causes EM radiation to be emitted. Hotter objects emit higher frequency EM waves. Higher frequency equals lower wavelength because we consider the speed of light to be constant, right? Or the speed of EM waves to be constant. And if the speed of EM waves are constant, then as we increase frequency, we decrease wavelength, right? By V is equal to F lambda. And so if hotter objects emit higher frequency, then our wavelength decreases, right? And if you remember, right, the color red has a longer wavelength, so a higher wavelength than the color blue. And that's oftentimes why we say if we see a blue flame, it's hotter than an orange flame or a yellow flame, right? Because a yellow flame is closer to the color red. And so the color yellow has a longer wavelength. So light of yellow color will have a longer wavelength than light of blue color. And so if an object is emitting, so a blue flame is essentially hotter than a yellow flame because it's emitting higher frequency EM waves. That's why it's appearing blue, right? And these EM waves are visible light, essentially. And potentially other frequencies as well, but that is for HSC, like module 7-ish. So you don't need to know that now, but that's kind of an explanation of why blue flames are hotter, because it's technically emitting a higher frequency EM waves. That's why it appears blue. So yeah, that's conduction, convection, and radiation. Now we can move on to latent heat. The definition of latent heat is the heat required to convert a substance into its different states without a change of temperature. And this is seen by areas labeled phase change in the below graph. So you can see how initially it's a solid, and then there occurs a phase change where it melts, right? And then it begins to build up heat again, right? So heat is beginning to build up as it changes from solid to liquid, right now to water. So it turns from ice to water. Heat builds up in the water, it builds up in the water, builds up, until all of a sudden it triggers another phase change. So it's like you're building up energy until you unlock a new level, basically. And the moment you unlock a new level, you undergo a phase change, and so water evaporates now, and gas kind of just keeps increasing in buildup of energy. Same way we can go in the other route, right? So we can take away heat, right? So we're taking away heat, and all of a sudden it unlocks phase change again, because now we're at that stage where it can undergo condensation. So it's lost all that heat, and so all of a sudden it's being demoted, right? So as it's being demoted, phase change, gas undergoes condensation, becomes liquid water. we can again begin to cool it down, or in other words, take away heat from it, right? So we're taking away heat, taking away heat, taking away heat. All of a sudden, it unlocks another phase change, and it begins to freeze. And then we can take away phase change, take away phase change, take away phase change, and it becomes solid ice. So that's how the concept of latent heat occurs. You can also look at thermal conductivity. Q over T is equal to Ka delta temperature, or change in temperature, over D, right? Using this, A is like the cross-sectional area, D is like the distance between the two things, right? Material having thermal conductivity is given by K, so K is the thermal conductivity of that particular material, Q is in joules, and T will be in seconds. So that's thermal conductivity. Q equals mc delta T now. That is an important formula because the formula is an all-time favorite for most, if not all, exams. So make sure you're comfortable using it and you understand what the symbols stand for. So Q represents heat energy in joules. M is the mass of heated object or substance. C is the specific heat capacity of that substance. In most cases, so the specific heat capacity of water is given in the data sheet, right? 4.18. So in most cases, they will test you on water. If they test you on other substances, they should give you what the specific heat capacity is, because it will be an unknown value and something that you're not expected to know as pre-known content. And then delta T is the change in temperature. So that's Q equals mc delta T, or Q equals mcat. So let's go through a question then. It's a hot day. You have a double-story house. State whether it is more efficient to turn on the air conditioner on the upper or lower level, and explain why. Okay, so let's go through the question then. Turning on the upper level aircon is more efficient. Why is it more efficient? Well, turning on the upper level aircon is more efficient because hot air rises and cold air falls. So a convection current forms, right? Just like how I explained it for the pan, hot air rises, cold air falls. So as the hot air rises, this cools the rising hot air on the upper level, right? So we establish a convection current, right? So if we have an air conditioner on the lower level, what we'll do is, as the hot air rises, we'll end up cooling the hot air, causing the hot air bit to become cold, right? And so then the cold air will sink to the bottom again, causing the cold air to heat up, causing that hot air to rise again, get cooled down by the AC, come back down, get warmed up, rise up again, get cooled down by AC, come down, and that cycle is going to repeat, forming a convection current, and that convection current is what's going to keep our house cool. So this cools the rising hot air on the upper level, which more effectively cools the entire house. So that's the best way to do that. So by the formation of the convection current, we're more effectively cooling down the entire house. All right, so next question then. A person holds a metal spoon. At first, it feels very cold to touch, but after 10 minutes, the spoon feels neutral in heat. Explain what has happened in this scenario. Okay, so again, take a minute to pause and answer the question, and then let's go through it. So originally, the system involving the cold spoon and the warmer hand is not in thermal equilibrium because our hand is going to be at a higher temperature than the spoon. And hence, this is why we feel like the spoon is cold to touch, because coldness, our sensation of coldness is essentially when we're giving away heat to another object. That's when something will appear cold. So over time, the system will reach thermal equilibrium now, with the spoon and the hand reaching the same temperature. Once they've reached the same temperature, there will be no net flow of heat anymore, right? So they will be at thermal equilibrium. Hence, the spoon will now feel neutral in heat because we're not giving away any heat, or we're not taking any heat in comparison to the hand. The sensation of hotness is generated by when we absorb heat from something else. That's the sensation of hotness. Sensation of coldness is when we give away heat. We give away heat when we come into contact with something that has less heat than us, right? So it's colder than us, and we take in heat to reach thermal equilibrium when we come into contact with an object hotter than us. So that's the sensation of hotness. So that is the answer to that question. And with that, we can now finally make a move on to module 4, electricity and magnetism. So structure of module 4 goes as such. We look at electrostatics, electric circuits, and magnetism. So 4.1, electrostatics. The inquiry question is, how do charged objects interact with other charged objects and with neutral objects? Okay, so in this one, students conduct investigations to describe and analyze qualitatively and quantitatively. And using the electric field lines representation, they model qualitatively the direction and strength of electric fields. They apply the electric field model to account for and quantitatively analyze interactions between charged objects. And they analyze the effects of a moving charge in an electric field in order to relate potential energy, work, and equipotential lines. Okay, so the main points of 4.1 summarized then. First, you understand electric fields and diagrams. Then you understand charge, and then potential energy and work. So, first thing is that like charges repel and opposite charges attract, right? And you can see here from the field lines that the field lines go from positive to negative, showing that they attract. So that's what the field lines would look like. Make sure you know how to draw these field lines in your exam. So the formulas go as such. In general, electric field strength is equal to F divided by Q. And the electric field strength between charged plates, in this case like this, is equal to negative V over D. Or just V over D if we're looking at magnitude itself. So the amount of arrows going in or out reflects the density or the amount of charge everything has. And in terms of drawing these, because you will more than likely be asked to draw these at some point during your senior years, make sure that these straight lines are spaced equidistant or like equidistantly. So that's an area where you could lose marks if one of them is way further than the other line. They should be evenly spaced out, right? And they should only be bending on like the last two equipotential lines. Everything else, draw them as like straight lines, right? Always draw with a ruler as well. So that's all the advice I can give for electric fields and diagrams, right? Make sure that these two, assuming they're the same charge, have the same number of field lines, right? So if one has plus 2C and one has plus 1C, make sure that the one with plus 2 coulombs has twice the number of field lines or twice the number of arrows than the other one, which is 1C or 1 coulomb, right? Because that's how we represent the magnitude of charge. So yeah, other than that, not much I can say about electric fields and diagrams. We can move on to charge now. So with charge, electric charge typically involves an imbalance of protons, positively charged, or electrons, negatively charged. And this is measured in coulombs. So the methods of charging objects, we can charge objects by friction. So this is where we transfer electrons from one object to another by giving it static charge. And we can also charge objects by induction. This is where we charge without contact. And this involves externally charging an object and a ground wire. So this is charging by induction. So first what we do is we have a metal sphere. A metal sphere will initially have positive charge and negative charges, right? A metal sphere has delocalized electrons, a sea of delocalized electrons, right? That's characteristic of a metal. So these electrons can move anywhere, right? So what will end up happening is these electrons, so as we put this ebonite rod that's charged negatively next to the metal sphere, electrons will be repelled from electrons, and so the electrons will accumulate on this end of the metal sphere, the opposite end to the ebonite rod. As electrons accumulate on this end, that will then, by consequence, generate a positive charge on the metal sphere on the side next to the ebonite rod. Protons won't be extracted to this side, but due to the net negative charge on this side of the sphere, it will produce a net positive charge on this end of the sphere. So what we can then do is, by using a grounding wire, we can extract the electrons on this half of the metal rod, right? We can extract all the electrons from this half of the metal sphere. And by extracting these electrons out, we are now left with only the net positive charge. And so we can say now that the sphere has a net positive charge, essentially. So like charges repel and unlike charges attract. By how much? Well, you can use Coulomb's law to figure it out. F is equal to 1 over 4 pi epsilon naught times Q1 Q2 over R squared. This is a constant value. So everything that's white is a constant value. It's given to you, except for force, obviously, because force is something that we have to find out ourselves. And black is representing magnitude of charges and distance between the charges that determines the force itself. So yeah, that's that content. We can look at now potential energy and work. So a moving charge in an electric field can be visualized by moving mass in a gravitational field. Equal potential lines are the lines above which are like gravity. moving an object to side does not change an object's gravitational potential, much like moving a charge side to side in an electric field. Only when you move it up and down along the equal potential lines does a transformation in electric potential energy occur. Same way with gravitational potential energy. Only occurs when we move it up and down. Right, and we can get volts is equal to change in potential energy over Q. That's how we can calculate volts. Or we can just use the formula that we used earlier, E is equal to V over D. So V is equal to ED. All right, so now we can go through 4.2, electric circuits. Query question goes, how do the processes of the transfer and the transformation of energy occur in electric circuits? So students investigate the flow of electric currents in metals and apply models to represent current. You investigate quantitatively the current voltage relationships in ohmic and non-ohmic resistors to explore the usefulness and limitations of Ohm's law. Students quantitatively analyze the rate of conversion of electrical energy in components of electric circuits, including the production of heat and light. Students investigate qualitatively and quantitatively series and parallel circuits to relate the flow of current through the individual components, the potential differences across those components, and the rate of energy conversion by the components to the laws of conservation of charge and energy by deriving relationships. And students investigate quantitatively the application of the law of conservation of energy to the heating effects of electric currents. All right, so the main points of this dot point is going to be parallel versus series circuits and a bunch of different laws and equations, unfortunately. So electric currents can flow through arrangements of wires called circuits, and this circuit must ultimately be a closed loop for electric currents to flow through. Conventional current, this is important, conventional current flows from positive to negative. And this is what we use most of the time. Even though it's electrons that are moving, conventional currents will flow from positive to negative. So electric current is modeled by I is equal to Q over T, given by coulombs per second. Voltage is given by V, capital V is equal to W over Q, or energy over Q. And it's given by volts, obviously. Voltage is also referred to sometimes as potential difference over here. Then we have Ohm's law, which is a relationship between voltage and current. It's given by V is equal to IR. I is current, measured in amps, and R is resistance, measured in ohms. And this one works for simple resistors. Complex resistors can be non-ohmic. So you can see over here that it doesn't have a linear relationship, whereas over here it should have a linear relationship because assuming that one of these components are kept constant, they should all have linear relationships, right? So this is evidence for non-ohmic reactor because resistance is always changing, whereas here resistance is kept constant. And so that indicates it's an ohmic resistor. So we also have formulas now for power, energy, and power and energy. So power is equal to a lot of formulas for power. P is equal to VI, which is then equal to V squared over R, which is equal to I squared over R. These formulas are kind of derived from the V equals IR, so you can sub in variations of this formula into power to get these different variations. It's measured in watts. And we also have energy now, which is equal to power times time. E is equal to PT, measured in joules. So the watt is then equal to 1 joule per second, power, right? Power is given in watts, E divided by T. Power is equal to a watt, which is 1 joule per second. Energy lost then in an ideal circuit, there is no energy loss. But in the real world, resistance all but small is in the wires and components we use. And remember that if energy is lost in a circuit, it is simply transformed, most likely into heat, right? So your wires aren't going to be screaming, so it's not going to be sound. It's mostly transformed into heat, right? Because energy can't be destroyed. It can only be transformed or transferred. And this is a result of non-ideal efficiency. So we also have two different circuit types. We have series and parallel circuits. And there are different ways of solving for resistance or the total resistance in series and parallel circuits. In series circuits, you can simply add them up to find the total resistance in a system. Whereas in a parallel circuit, you have to find 1 over the total resistance in a system by adding them up in this fashion, and then or flipping the fraction after you find this value. So you divide everything by, so you do 1 divided this value to flip it around, and then you can find the resistance in the total system. All right, so we also have conservation of Kirchhoff's laws. So it says that the net voltage is equal to 0, and this applies around any series loop. And conventional direction is positive to negative. That's another thing that we looked at earlier. You also have Kirchhoff's current law. So that is the total current is equal to 0 in the system, and that applies at a node or junction. Positive is defined either pointing towards the junction or pointing away from the junction. Right. So now we have dot point 4.3, magnetism. So how do magnetized and magnetic objects interact? So in this inquiry question, summary is just basically looking at magnets itself, understanding the basic rules of magnetic field lines and common magnetic objects. So we have ferromagnetic materials. These can be turned into permanent magnets by rubbing a magnet over it in the same direction many times. And the strength of the force depends on the magnetic field strength and distance away. And then let's look at magnetic field lines then. These run north to south. They never cross. That's very important. Always run north to south and they never cross. And the closeness of the lines relates to the strength of the magnetic field. And we can use right-hand rule for wires and solenoids. So with solenoids, to find the direction of the magnetic field, we look at the direction of current. So if current in this case, right, in this case, current is going to be going downwards, right? So it's going to be going downwards. So it's down, 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 because we can follow the direction of current in this current, right? So we point our forefingers downwards, right? As we point it downwards, we can see that our thumb is pointing out of the page. So if my thumb is pointing out of the page, that indicates that the direction of the magnetic field is going to go out of the page. Now, if we look at this picture over here, you can see that it's going in a similar direction to which my thumb pointed in. So if I orientate my thumb properly, it will point in the same direction of the magnetic field lines. So that's how that works. All right, wires and magnets. So a current through a wire produces a magnetic field around it, and this is modeled by B is equal to mu naught I over 2 pi r, where B is magnetic flux density measured in Teslas, I is current, and R is the distance away from the wire. We also have coils of wire, aka solenoids, and this is modeled by B is equal to mu naught Ni over L. N will represent the number of turns in the solenoid, L will be the length of the solenoid, and N over L will represent how tightly packed the solenoid is. And these are called turn density. So a couple of formulas that you guys would just have to remember with module 4 at least, but applying them should be relatively easy as long as you know what all the values mean. Right, so questions can trip you guys up by asking you to solve different values. But for these types of questions, exposing yourself to a variety of questions is what I believe to be the most effective way of approaching this. But yeah, other than that, if you guys have any questions, make sure to put them down in the live chat, and I will be there answering these questions for you guys. But other than that, I hope you enjoyed the lecture. It's been a pleasure going through this lecture with you guys. But yeah, good luck with your year 11 yearly exams, and have fun in your HSC year in the future, and good luck entering HSC as well. But yeah, other than that, I'll see you guys later.